In this lesson, we're going to talk about one of the more commonly tested aspects of arithmetic for the executive assessment, division and factoring. So let's take a look at this sample division problem using the long division format. And one of the things that you have to recognize as we're defining division is that really long division is just bad marketing. It really doesn't take that long, and there are a lot of unique aspects of it when it comes to the parts and moving pieces of division that the exam really likes to test it. So we've got 17 being divided by 5 here. So to manipulate this, we know that we multiply 5 times 3 because 5 goes into 17 3 times. Then we subtract out the 15, we get 2, and we know that our result is going to be 3 with a remainder of 2 because 5 goes into 17 3 full times, but then you've got 2 left over for the last little bit of the final 5. So we know that the quotient is the 3. It's the result of division. We know that the 2 here is what is known as the remainder. The 5 is our divisor or factor, and the 17 is what is known as the dividend. So these pieces, the values themselves can change, but the placement of the definition of terms does not. So these are the things that you need to be able to define whenever you look at division when it's being broken down in a kind of savvy way for this test. So there are 4 different ways that we could write out 17 divided by 5 using varying notation. So the first is obviously what we already have, which is that 3 remainder 2 thing. Now, you can also write what is known as an improper fraction, and that's just 17 as a numerator and then 5 as a denominator. We can also write it as a mixed number, which is 3 and 2/5. But a little pro tip is that on the executive assessment, you're basically never going to want to use mixed numbers unless the answer choices are presented as mixed numbers as a final step through conversion, because you really can't calculate a lot with mixed numbers. And as a decimal, we know that 2/5 will convert to 0.4 because that's equal to 4 out of 10. And the decimal system is all based off of multiples of 10. So our decimal would be 3.4, not 3.2. And that's an important distinction. So let's talk about how remainders work, because that's the thing in the division that makes it most complex for people. So our remainder, we know that our remainder has to be between 0 and the divisor. You can't have a remainder that is greater than your divisor. For instance, if I'm dividing by 5, I can't have a remainder of 7 because, in fact, we would then have to increase the quotient. Because if we say upped 17 to 22, well, 5 is going to go into 22 4 times, not 3 times. So then you'd still have a remainder of 2, but it would be after subtracting out 20 from the then 22. So if the remainder is equal to the divisor, you have to actually add 1 to the quotient, and your remainder is going to reset to 0. And your remainder over the divisor is your decimal left over as a fraction. So that's how we got 2/5, because we have 2 remaining out of the 5 that was left over. And we know that the remainder over the divisor is how we got the exact decimal conversion of 3.4 as being the decimal result of 17 divided by 5. Now, here are some really handy divisibility rules for integers so that you don't have to fully calculate if they're asking you about just if something is divisible. And it's really helpful if you're looking at logically estimating for potentially larger mathematic calculations. So first is a bit of a trick question, because for the purposes of the executive assessment, nothing is divisible by 0 because the result is infinity, and that's a non-real value. And as we discussed in our number properties lesson, infinity is not tested on this exam because all of the values on the executive assessment are considered real for the purposes of the arithmetic. But everything is divisible by 1 because anything divided by 1 is just itself. We've talked about that too. Now, knowing that something is divisible by 2 is simple as just seeing whether or not the units digit is even, because if the units digit is even, the whole thing is even. So if I want to determine whether 284 is divisible by 2, well, I know that that final units digit is even 4, so the whole integer has to be even. Dividing by 3 has a unique little trick. It's that the sum of the digits is divisible by 3. So for instance, if I want to know whether 96 was divisible by 3, well, I'd take 9 and I'd add it to the 6, and I'd go 9 plus 6 is 15. 15, of course, is divisible by 3, so the integer 96 is divisible by 3. Conversely, if I consider 95, well, 9 plus 5 is 14, and 3 does not go evenly into 14. So that's a handy trick to determine whether an integer is divisible by 3 or not. Now, for 4, you just want to test if 2 divides evenly into the integer an even number of times. So, for instance, with 96, if I did the math there and I said, well, 96 divided by 2 is 48, well, since 48 is even, I know I could just have that and figure out how many times 4 goes into the integer 96, and that, of course, would be 24. So, generally, if you're testing your factors in such a way that you need to test divisibility, you're probably going to test it all the way through. So you could just determine whether 2 divided into that integer that you're testing an even number of times to see if 4 is going to be a factor as well. For dividing by 5, all you have to see is whether your units digit is 5 or 0. For 6, you just take the rules for 3 and 2, because if you have an integer that is divisible by both 2 and 3, it has to be divisible by 6. So if you have an even that has a sum of the digits divisible by 3, then you're guaranteed that the value is going to be divisible by 6. And sure enough, if we looked at our 96 again, we'd find that 6 goes into 96 exactly. That's going to be what? 1 time, and then 36, 16 times. So 16 times 6 is going to be 96. For 7, you're going to have to long divide. There is a really wonky way to deal with 7 in terms of divisibility, but it's not really a shortcut. It's going to take you longer than just doing long division. We've already established long division is really just bad marketing, so long divide if you have to test the divisibility of 7 for any problem. For 8, it's the same rule for 4, just extrapolated. So if 4 divides evenly into an integer an even number of times, that integer is also divisible by 8. For 9, it's the same rule as 3 extrapolated. So if the sum of the digits is divisible by 9, for instance, 189 is divisible by 9 because we know that 1 plus 8 is 9 plus 9 is 18, and 18 is divisible by 9. So 189 itself is divisible by 9. And lastly, of course, is the idea that if you have a units digit that is 0, you've got something that is a multiple of 10 and thereby divisible by 10, because you could just remove the 0 to divide out a multiple of 10. So how does this play into the exam? Well, all factor pairs is the first way. So if you need to determine things like greatest common factor, this is what you would do for the two values. So let's just consider 72. So the first factor pair for all numbers is 1 in itself. So we've got 1 goes in 72 times. So 1 times 72 is 72. Then we just test our rules. So 2 is going to go into 72 because 72 is even. And 2 times 36 is 72. We know that 7 plus 2 is 9, so 72 is divisible by 3, and 3 goes into 72 24 times. Now, we know that 2 goes into 72 36 times. That's an even number of times, so 4 is going to work too, and we can see the proportionality at work here, because 2 times 2 is 4, so I have to divide the 36 by 2 to get to 18 to determine that 4 goes into 72 exactly 18 times. Now, then we've got 6 and 12, because 5 doesn't go into 72 because it doesn't end in 0 or 5. Now, 6 goes in because we've got a2 and a3 that already go into 72, so we know that 6 has to go in exactly 12 times, and we can see that same proportionality at play because 2 times 3 is 6, and 36 divided by 3 is 12. And then 7's not going to go in because 7 times 10 would be 70. 72 is not 7 more than 70, so that's not going to work. But 8 will go in exactly half the amount of times as 4, and 8 times 9 is 72, of course. So now, you can see that as soon as you hit the bottom and start working your way back up the other side, you are done with your factor pair. So as soon as we hit 8 times 9 is 72, we don't have to test any further. And there are some facts that will help with this as well. We know that the greatest factor is equal to the least multiple, which is equal to the number itself. We saw that before. So we know that 72 is the largest factor of 72. It's also the least multiple of 72, and it is 72. Simple enough. We know that once a possible factor squared becomes greater than the dividend, that's the number that we're testing as what all of these factors are dividing into, all the factors have been identified. So how does that play in here? Well, we know that the nearest perfect square greater than 72 is 81. So 9 squared is greater than 72. So each factor pair of 72 must include a value less than 9, because 9 times 9, and any two numbers larger than 9 will be bigger than 72. So that means that as soon as we hit 8 and 9, we don't have to keep going. And our least common multiple is the first multiple common to two integers. And the greatest common factor is the largest factor common to those two integers as well, just by definition. So we've talked about our all factor pairs. Now let's talk about our prime factor tree. So 72, if we want to prime factorize it, well, we're going to split it into its most equitable pair of factors, in this case, 8 and 9. So we know that 8 times 9 is 72. Then we keep splitting those factors up until we hit primes that cannot be any further factor. So we know that 8 can be split into 4 and 2, and 9 can be split into 3 and 3. Now, only 4 can still be split further down, and 4 could be split into 2 2s. And we know that every number has a unique set of prime factors, and prime factors are simply integers greater than 0 that have exactly 2 factors, one in itself. And every integer has a unique prime factorization. For instance, 72 is the only number that is comprised of 1, 2, 3 2s and 2 3s. And the prime factorization of 72, written using exponential notation, which is probably the most common way that you'd see it, is 2 to the third times 3 squared. So any integers with 3 factors of 2 and 2 factors of 3 will be divisible by 72. So you have 2 factors of 3 and 3 factors of 2, and say a factor of 11, still going to be divisible by 72. And any integers with fewer than 3 factors of 2 and 2 factors of 3 and equal to as well are going to be factors of 72, because of course 72 itself is a factor of 72. So if we had 2 times 2, 4, that has fewer than 3 factors of 2 and 2 factors of 3, it's going to go evenly into 72. And one thing to note about primes just by definition, 1 is not prime. 2 is the first and only even prime number. And the way we know this as a proof is that 1 has exactly 1 factor itself. It doesn't have 2. And prime integers have 2 factors. So very careful when you encounter prime numbers on the test. Don't assume that 1 is prime. In fact, it is not. So let's go on over to the whiteboard and see how division and factoring can be tested through sample problems to get you ready for the executive assessment. Here we have a sample problem-solving question. As always, we're going to set up the scratch pad first, listing our answer choices A through E. We have simple numbers, so I'd probably encourage you to write those out as well. We've got 2, 3, 8, 9, and 20 as our answer choices. And we're being asked for something very unique here, a possible remainder when x is divided by y. So one thing to note is when you see some value that is non-specific being sought, you really want to consider logical evaluation. So this is a logical evaluation clue. And we're going to have to do some technical math as well to solve this using what we just learned about remainders. But this makes you think that I have to consider the concept, not just directly solve using calculation. So we have the question, if the result when integer x is divided by integer y. So I'm going to do the long form. So we know that y divides into x, and we get 36.45. And we're being asked for what is a possible remainder. Well, we remember from the lesson that our decimal left over as a fraction is equal to our remainder over our divisor. So we can fill in this equation. First part we have to do is convert that 0.45 to a decimal, and that is just going to be 45 over 100. Keep it simple. I don't need to simplify that just yet. And that's going to be equal to the remainder, which we don't know. We'll just write that as r. And then we've got our divisor, which is the y. So we know that if we cross multiply here, 45y has to equal 100r. And everything has to be an integer because we were told that we started with integers. And if we were to divide the whole thing by 5, because there's a factor of 5 in both 45 and 100, we discover that 9y has to equal 20r. So what is our possible remainder? Well, we know that our remainder, first off, has to be a multiple of 9. And because 20r, our remainder, is the value, and we're not going to get a divisor of 9 from 20, so we know that no matter what, our r must be a multiple of 9. And the only answer choice that is a multiple of 9 is choice D. And I don't want to fully calculate. I just know that logically that must be the case, looking at the relationships and understanding that there's no multiple or a factor of 9 within the 20, so it has to be in the R, and that tells me that R has to be a multiple of 9, and our correct answer here will be D through logical evaluation using that technical representation of the relationship between remainders, divisors, and those decimal leftovers. So now let's scroll on down and take a look at a data sufficiency example. So as always, we start with the question. We're being asked, is 25 a factor of a squared? And this, of course, is a yes-no data sufficiency, so we'll just box that off so we don't lose sight of what we're being asked for. And we want to break this down as part of our need to figure out what exact factors have to be part of a squared. And so for 25 to be a factor of a squared, we know that 5 must be a factor of a. Because whatever you have a as, when you square it, is going to give me that factor of 25. So we could square root both, consider the factorization, and go, well, we need to determine definitively if 5 is not a known factor of a. So condition 1 says a is a multiple of 3, and we could just represent that as a is equal to 3, we'll say m. Well, I don't know whether m is or is not a multiple of 5, so I can't determine whether 5 is a definitive factor of a because I don't know, basically here, what are the factors of m. We have no idea. 5 could be in there, it might not be in there, and you're in a better position to just consider it abstractly rather than fully plugging in here. We just know that m could or could not be a multiple of 5. I've got no limitations. So that means that choices A and D are eliminated because condition 1 alone is not sufficient. And then condition 2, we know that A is not a multiple of 5. Well, that is exactly what we needed to know. And if we considered it at the outset, we now know that 25 cannot be a factor of a squared, because if a is not a multiple of 5, a squared is only going to have the factors that were included in a, just doubling the number of them. So this tells me that my answer is always no. And that 25 can never be a factor of a squared if a itself is not a multiple of 5. So alone, condition 2 is sufficient, and our correct answer must be choice B. So consider these concepts of factors, divisors, and divisibility generally as you work through some of the more unique and kind of clever number property style problems that you encounter on the executive assessment to really maximize your score by practicing problems such as these ones.